name is Omar Mikawi, and I am joined in the chat by a few of my colleagues here at Bryan Research Engineering, in particular Mr. Jo Kim Soo, Mr. Ganak Srivastava, and Mr. Di Wu, and finally Mr. John Chan. Let us go ahead and get started. So today's webinar will be focusing mostly on production facilities, some basics on modeling it, and how ProMax can help with certain projects. This is a brief overview of the upstream world. It can generally be divided into 4 main sections, with the facilities engineer, production engineer, reservoir engineer, and environmental engineer groups. Each of these groups kind of overlap with each other in terms of how they benefit and hurt each other. And historically, ProMax has been used by facilities engineers and environmental engineers, and we've been used extensively by those 2 types of engineers. With new tools that are coming out and are currently out, such as the IPR tool, we are venturing into the production and reservoir engineering side of the equation. For example, in production engineering, we have added an IPR tool in order to model some of the inflow performance of your reservoirs. And in the next release of ProMax, we hope to have our PVT tool, which is a PVT analysis tool that allows you to replace the need for having a PVT report generated every time you want to see differences in your facility. But for now, let's talk about the current features of ProMax. So here is a basic production facility with 3 vessels, a slug catcher, a HP separator, and an LP separator into a stabilizer. So certain things that you may want to pay attention to as you're going on in this session is parameters that affect not only the production of the facility in terms of how much gas is being produced, how much liquids or condensate is being produced, but as well as whether or not the facility can operate safely and effectively, taking into consideration your downstream requirements of pressure. So in the vessels, the main 2 things we might be concerned with are pressure drop and how accurate those are, and whether or not there's entrainment in the system. As it is right now, entrainment in ProMax is more representative than predictive. And by that, I mean, we don't currently have the capabilities of predicting what the entrainment in a vessel will be, but we do have ways to represent what would happen if an entrainment in a vessel was at a certain point. So the benefit of this is that your downstream units, such as your stabilizers, your tag, your strippers, will have a more accurate representation of what's going on. So if you have entrainment in your upstream vessels where you have some of your heavy liquid or your produced water going out with your hydrocarbons, you can model that in ProMax such that your stabilizer can be modeled as a 3-phase tower. And ProMax has wide capabilities with modeling 3-phase systems and 3-phase towers in order to improve accuracy. Some things we want to note when we're modeling stabilizers is what's our basis of design? What is the point of this stabilizer? Is it to adjust for volatility? We're concerned about emissions in our stock tank, and so we need to hit a particular RVP spec. Or are we worried about acid gas content, where we have a particular H2S content we need to reach in the stabilized oil, and we're using our stabilizer in order to boil off as much as of those condensed or dissolved gases as we can. This is where the entrainment becomes very important for the accuracy of your results. Because as we all know, the heavy liquid portion has its own saturation point with acid gases and its own thermodynamic properties with acid gases. So the ability to model a 3-phase tower where you can see your water phase, your hydrocarbon phase, and your gas phase all interacting with each other and all performing mass transfer on each other allows you to generate a more accurate system in order to figure out what is the reboiler duties you need to run the system effectively and to hit your product specs. The next consideration that ProMax can help you in is your breathing emissions. Now, we do have an air emission stencil, which is a simplified tool that allows you to also calculate not only breathing emissions, which is the emissions that occur just from natural losses to the atmosphere over the lifetime in the tank, but that stencil also allows us to measure working losses as well, the losses associated with filling the tank. One thing to note about our air emission stencil, however, is that it is based around calculation methods provided by the U.S. Environmental Protection Agency. So the U.S. Environmental Protection Agency has a set of equations that it requires its all hydrocarbon processing companies to use when calculating its emissions from their tanks. And our tool uses that equation. That may not apply for how your local emission registry does their analysis. So I would take that into consideration. If your internal emissions are based off the US government's EPA standards, then the air emission tool will be fantastic in order to calculate the working losses. If not, then the basic ProMax thermodynamics, in particular the gas phase coming out of our tanks, will be more than enough to figure out the breathing losses from our tanks, just the natural losses to the atmosphere from the oil sitting there in the tank. As with every model, any model is only as good as the information that is inputted to it or provided to it. So we can generally, or I like to generally separate our hydrocarbon components into two parts, our light ends and our heavies. And these are arbitrary metrics. Light ends don't necessarily need to end at pentanes, and heavies don't necessarily need to start at C7. It could vary from place to place, and some places may say that the butane is considered as a heavy. But in general, from C1 through C5, these usually come out in our PBT reports and our reservoir samples as pure components. They tell us that it's methane with a defined molecular weight. It has a defined specific gravity. We know exactly what it is. This is absolutely methane. And then ethane, the same thing, propane, the same thing, so on and so forth. As we get heavier and heavier into hydrocarbons that normally wouldn't appear in large quantities in the gas phase, it becomes more difficult to parse out what it actually is. So as you guys may know from your PBT reports and your analyses, they no longer get represented as pure components, but instead they get represented as pseudocomponents. These pseudocomponents may be mercaptans, they may be our heptane pluses, our octane pluses, or even bitumen. So we don't know what is in each of these components, and we don't know what their properties are, but we do know some properties. For example, the molecular weight and the specific gravity. ProMax allows us to add these components into our system as single oils, or oils in general. There are two types of oils, which we'll discuss in a minute, but they'll be added in as oils. So pseudocomponents can be added in as oils, and pure components exist naturally in our ProMax environment, and we can simply take those information from the environment. So the two types of oils that appear in ProMax, there are curve oils and single oils. Curve oils are more common in refinery settings and downstream settings. They're D86 or TBP curves. They're sometimes used in upstream settings, depending on how your lab reports its results. It defines the light ends as pure components. So if you look at the curve oil tool, and we'll demonstrate it in brief in a few minutes, it'll give you an option to define what your light ends are, and you tell it that it's methane, ethane, propane, N-butane, I-butane, et cetera, and then the heavier components are defined as temperature cuts. So in the curve, you'll simply say what the volume boiled off or the volume fraction is, and set those temperature cuts. So when you see the composition in ProMax, the heavier components will be shown as the 200 Fahrenheit temperature cut, or the 300 Fahrenheit temperature cut. The other option of defining an oil is, instead of using a curve oil where you define your entire reservoir, right? So a curve oil would be used to define the entire reservoir as a single system. The single oils allow us to define particular components of the reservoir. So how this would work is we would use the single oils to only define our heavies. We would input the molecular weight and the density of these single oils. And then these created single oils need to be added in as independent species. And by that I mean, when we create a C7 plus oil and we go to our environment, we need to go in there and select C7 plus and add it. For the curve oil, the entire oil comes in one go. For the single oil, we need to individually add in the single oils that we have created. There are two types of samples that we can use. So now that we know how to represent the information, it also matters how we get our information. One type of sample is a downhole sample, where we take the sample before it goes to any type of separation, and then we try to quantify its contents. If we're able to get an accurate downhole sample without any type of flashing occurring, we could simply take that downhole sample's compositions and input it directly as our well stream fluid. The other type of sample is samples taken off a test separator, where we take some of the vapors and some of the oils from the test separator and then recombine them. Each of these type of samples have their own advantages and disadvantages, but in general, sampling have issues. And the common issues across both types of samples is after you've taken the sample from a downhole system, for example, you could have leakages. Any leakages in the sample mess with the thermodynamics and the equilibrium of the sample. With a poor thermodynamic equilibrium in the sample, we cannot get an accurate representation of the context of our system. We could either have our oil be too heavy or our oil be too light. Another issue could be contaminants. We could have external contaminants enter our sampling vessel. And then issues could also happen in the lab. So we could have non-equilibrium at the sampling location. For example, if our test separator is not, so to speak, always on, it needs to have the oil diverted from its standard system to go to the test separator. The test separator may not be operating at a steady state equilibrium yet. And if you take a sample at non-equilibrium state, that messes with the accuracy of the sample. Another thing that could happen is in the lab itself. Usually when we have a gas and an oil sample, the lab recombines the two systems and waits until equilibrium is met in order to do its analysis. Sometimes these labs don't wait long enough for this equilibrium to be established because it's a very long process and it's hard to figure out exactly when that can happen. This non-equilibrium state can also lead to some inaccuracies in the system because it could be over-representing some components in the liquid phase and under-representing components in the gaseous phase. And then finally, the most egregious of these errors is a failure to detect certain components. Your lab may not even look for certain components in a system. It's very common in the Middle East to have extremely sour fields. There are some labs out there where when you take your sample from your system and they start measuring how much is in the liquid and how much in the vapor, these labs don't even check what the content of our acid gases in the liquids are. So they say that there's 0 acid gases in the liquid. There's 0 H2S and CO2 dissolved in the liquid phase of the sample. We know from experience that that's not the case. We have entire facilities dedicated in order to remove acid gases from the liquid phase, particularly stabilizers that are used to strip out H2S. So if our lab is telling us there is 0 H2S in the liquid phase, that can lead to a severe underreporting to the overall H2S content in your system. So to deal with these, we're going to show you on ProMax how to account for these errors and what different types of errors can do to your final result. The last thing I want to talk about, now that we've talked about considerations to do inputs into a model, and we've talked about how to define our well stream going into our model, I want to talk about what the benefits of having a model are. So one of the benefits of a model is allocation. We'll be going into how to do allocation in a few short minutes, but as a general idea, here is a production facility that has 4 different fields entering the system. Say these 4 fields come from different companies or different sources, and you want to figure out, based on your final exports for your condensate and your gas, how much to pay each of these fields. Using ProMax, you can set up an allocation report for it to tell you how much of the gas comes from, say, field 2, and how much of the condensate comes from field 2 in order to pay that field the appropriate revenue. Another advantage is not only can it tell you how much of these streams come from each field, The allocation report can also tell you what is the source of the individual components. What if you want to figure out how much of your acid gas is coming from a particular field, that you're charging a field for usage of your treatment system? You can figure out using our allocation report, and we'll be showing it briefly in a few seconds, how much of the H2S in our gas comes from field 3 and how much comes from field 4, and the same thing for our condensate. So having an accurate model with the entrainments, the pressure drops, the whole 9 yard inputted to a satisfactory degree can allow you to do these type of application reports where if you are just using a test separator, which doesn't properly account for all the system hiccups that may be occurring in the streams and all the differences in thermodynamic changes that can happen in terms of pressure drops in these systems, may not accurately give you a representation of what your actual allocation is. With that, let's jump into the actual ProMax side of things and discuss in order our sample definition, our model creation, and our allocation report. So here is a pre-made ProMax file that I have created for you guys. I have 3 types of samples that I am recombining in the system. Let us say that these samples are test separator samples where we took a sample of the gas of the test separator and the liquid of the test separator, and we're recombining them in the system to figure out what the actual well stream composition is. I want you guys to note that depending on your lab, this process may also be and will be used to define your downhole samples. Because a lot of the times what labs do, because the downhole sample is taken at such a high pressure, is that they would first flash that downhole sample, take the gas and the liquid, and then do the analysis in terms of the content on the individual gases and liquids and recombine them. All right. Very rarely do labs directly measure the downhole sample. So first things first, as with any ProMax model, we need to define our environment. What is the components of our system? The methane, the ethane, et cetera, et cetera. So if you hop on over to the active environment, I am using a standard Peng-Robinson environment. And in the components tabs, there are 2 sets of components. There's available components, which are the pure components that are naturally in ProMax. So as you can see, hydrogen is in here. We have helium, water, etc., etc. So these are the pure components that are existing in the system. So our methanes and our ethanes, so on and so forth. Oils, as I said, the upstream facilities have pseudocomponents, will appear down here. As you can see, it's blank because I've already added in all of my oils. So if you see the C7 star, the C8 star, the C9 stars, these are my oils, and I've labeled them as such. So let's take a look at how to add an oil to our environment system so that we can add it to the installed package. To add an oil, we need to hop on over to the oil button. It is under active flow sheet. Here are all the oils that are available in my system. But if I hit the edit oils button, it gives me a dialog box with an option to add either curve oils or single oils. So starting with curve oils, you would simply select your assay type, TBP or D86 or the other assay types available. And then you would hit edit on the right-hand side and put your boil-off curve. So 10% at 30, 20% at 50, so on and so forth. You can then change, depending on the curve that was created, we will create what is called property curves, so the specific gravity across the volume fractions, molecular weights across the volume fractions, and so on and so forth. You can install your own curves for that as well. You can also enter light ends into your system. So in here, I can say that there is a methane light end, an ethane light end, so on and so forth. This is advantageous when we are trying to represent our entire well stream as a single oil. And then once this curve oil is added to the system, we can then add that curve oil wholesale into our environment. another feature that I would like to share with you guys, and this is useful for some quick oil generation, is condensate mode. So under condensate mode, instead of putting temperature, you would instead put carbon numbers. So if I wanted to say that I had carbon number 7 through 36, it will create a curve from 7 to 36, and all you need to do is put in the associated volume fraction. So this is great in terms of having a quick and easy well stream definition, but its disadvantage is that you have very little flexibility with changing the specific gravity and the molecular weights of your C7 cuts, your C8 cuts, so on and so forth. So I generally recommend, instead of using condensate mode, if you have individual cuts and individual pseudocomponents, to use the single oil. What is the significance of light ends in modeling the oil stream? Okay, so the curve oil tool is not modeling just the liquids of your well stream. The curve oil tool will be used to model the entire well stream, light ends and heavies combined. So instead of defining light ends separately and heavies separately, the curve oil allows you to do it all in one go. The single oils, which I'll be showing you in a minute, is what you would normally do to define our heavier components. Because you're absolutely right. Normally, we don't define light ends in the oil stream, but this gives you an option to do that if we have a D86 or TVP curve available. So the more common method is to create a single oil. So as you can see in my single oils, I have from C7 all the way to C80 in single oils. So let me add a new single oil to show you guys what our dialog box looks like. So when I hit a new single oil, this is the information it asks for. I can label the oil to be whatever I want. For now, I'm going to keep it a single oil 1. And this is something that you guys might be familiar with. We simply input a molecular weight and a specific gravity. And based off that information, it generates the rest of the properties relevant to the system. It generates the critical temperatures, the critical pressures, and all the other properties that could be necessary. Each of these properties are editable. For example, if you're not satisfied with your high temperature or your low temperature viscosity points, you can go in and change that number. Instead of 0.65, my high temperature viscosity is actually 0.68. I can go in and type in that change and have that be applied. So once I hit OK, my single oil is now created as an available oil, but that does not mean that it exists in my environment. What I then need to do is hop into the active environment and add that single oil to my component. So if I double click this, now the single oil 1 exists with the rest of our components. Let's take a look at how these recombinations occur. So here are what I call wet samples. If I pop into gas 1, I have a composition. As you can see, single oil 1 is not there because I've removed it. This is the composition of my gas phase, and it has some water in it. And here's the composition of my liquid phase. It also has some water. I'm then recombining this system. If you guys are ProMax users, you will note that I have a calculator on the flow of my gas stream, and I also have a calculator on the flow of my liquid stream. What this calculator does is that it accounts for discrepancies in equilibrium. All right, so what I've done is I've taken my lab. My lab has told me that the composition of my gas phase is these parameters. It's also told me that the GOR of the system is, in this particular case, 242.82. Let's say that the GOR was 242. So what I'm doing with this calculator is that I do not trust my lab to accurately give me the correct equilibrium compositions. So I am going to use these solvers to modify the flows of my gas and liquid to get what the true equilibrium in the system is. according to the GOR. So it's basically what piece of information do I trust more from my lab? Do I trust my composition analysis when I know that labs can sometimes overestimate or underestimate certain components or not even measure certain components? Or do I trust the volumetric or the flow measurements? I am more trusting of the flow measurements, so I'm going to set this up in such a way to iterate the gas and the liquids such that they can recombine at the accurate GOR. Once they recombine in the accurate GOR, this is where they separate again, and this is now the equilibrium composition of the gas and liquid streams in the lab. So here's the combined well stream, and here is the new equilibrium composition of the gas and liquid. So let me show you guys the differences that can occur due to equilibrium mismatches. So on the left-hand side, we have what the lab tells me the equilibrium composition is. On the right-hand side, we have what ProMax tells me the equilibrium concentration is. As we can see, there is little discrepancy when it comes to the lighter end components. It's almost bang on point. The heavier we go, however, the more discrepancies we see. For example, it tells us that we have 0.611 of C9 star, but in reality we have 0.615. So this is the predicted equilibrium concentration. So what we're doing with the separator is comparing the lab's equilibrium that it tells us these gas and liquids are at with what ProMax says the equilibrium is at, and using that information to recombine the system to get an accurate well stream composition. This is more useful when we have dry samples. We do the exact same equations here, where we have our solvers to get us our accurate TBP curves, and then we will calculate what the outlet equilibrium is in order to get the well stream fluid composition. The final thing I want to note is that, and this is the most important step, is if our lab excludes certain compositions. Some labs don't even detect heavier than C7 in the gas, and some labs don't detect acid gases in the liquid. So as you can see, this liquid is at 0 acid gas content. If we were to remix these streams, the liquid in my lab, the lab told me I had 0 H2S. So let's take a look at the liquid outlet. ProMax disagrees with the lab. Instead of 0 H2S, we think that there should be 0.1% of H2S in our liquid stream. That 0.1% is a proportion of liquid that is no longer measured in the lab, and it's also a portion of our H2S content that is no longer measured in the lab. So if we just took the lab's information and said that their recombined well stream was the accurate well stream, we would be under predicting the amount of H2S content going into the system, because the lab thinks there's none in the liquid when ProMax thinks there's 0.1. So that's why these solvers are important. I don't trust my lab to get accurate equilibrium data, but I trust ProMax to get accurate equilibrium data. What I do trust from the lab is to get accurate flow information so that they can give me what the GOR is. Using that GOR, I will adjust the flows of my gas and liquid that are measured from the lab to recombine into the well stream to get me an accurate well stream composition with accurate equilibrium composition. Let me modify this system to show you the difference that would occur in composition when we don't do this. So I'm going to take a quick snip of our current composition. This is the composition that is available to us when we do this process of using ProMax's equilibrium capabilities to model an accurate well stream composition. What I'm going to do now is I'm going to say, hey, the lab's 100% right. Everything they've told me in terms of the content, everything they've told me in terms of the GORs and the compositions, that is accurate, and I am simply going to input that information as is and not modify the system at all. So to do so, I am going to disable my iterators. and let's compare how different the results are. So now all we're doing is a straight recombination. No modification, no nothing. We're just recombining what the lab told me exists. So let's take a look at the well stream composition. First thing that you'll notice is our H2S content discrepancy. Next thing that you'll notice is a discrepancy in our light end content. So they're at small percentage points, true, but these small percentage points scaled up to millions of scuff a day can lead to massive ramifications downstream. So these small differences in content can lead to massive differences in how you would operate your facility accurately. So making use of these calculators that allow us to target the GOR of the system to account for errors in equilibrium allow us to make sure that we have the most accurate input to our model as possible. And I would say that 75%, possibly even 80% of the work when it comes to an upstream facility model is this step, getting an accurate well stream composition and accounting for lab discrepancies. The rest of the systems are trivial in comparison because if your inputs are wrong, your outputs are wrong, your deductions are wrong. So from that, let's take a look at a solved facility now. So this is a very rudimentary facility. All I have done is I've taken my well stream fluid and I've sent it through a few vessels. Each of these vessels have an arbitrary pressure drop. It's 30 bar in the first vessel, 20 bar in the next vessel, and finally 25 bar in the final vessel. I have defined this system instead of by inputting the pressure drop, by instead inputting the outlet pressure or the operating pressure of the system. So you can do either. You can either input the pressure drop or you can put the operating pressure. To put the operating pressure, you simply need to go to one of the outlet streams, either the gas or the liquid or the water stream, it doesn't matter. They're all at equilibrium, so they're all going to be at the same pressure. And you can type in the operating pressure of our vessel. So our slug catcher is at 70 bar, our HP separator is at 50 bar, and our LP separator is at 25 bar. All right, so I've inputted these numbers directly. You can tell from the white background and the blue text. And it calculates as is, and I have associated compressor station. Now, you may come to me and say, hey, what about entrainment? I know that it is not a perfect separation. ProMax assumes that it's perfect separation in these systems, where all the gas goes with the gas, all the liquids go with the liquids. If you do have an entrainment, you can hop into the vessel, and under process data, you can go to entrainment, and you can add an entrainment. You can add from any phase to any phase. So if it's liquid in the vapor, like you have droplet entrainment going out with your vapor phase, you can add that in. But more commonly, if you have water entrainment or liquid to liquid entrainment, you can have heavy liquid into light liquid, and then you can change what the basis is. So there's mass per volume. If it's a percentage, which is commonly the case, you just do volume per volume. So a volume per volume, and if it's, say, a 3% entrainment, you can do 3 out of 100. So that means that 3 liters of my heavy liquid goes for every 100 liters of my light liquid. So effectively, a 3% entrainment. And you hit active, and that allows us to set the entrainment. There is also an option to do a fraction from phase. So if instead of doing the calculation of 3 out of 100, you can say a fraction from phase, and you can simply hit the percentage. So 2%, 3%, 5%, whatever you would like. Set that entrainment, carries on through your facility. Again, this is important because ProMax has the capability of modeling three-phase stabilizers. To model a three-phase stabilizer, you obviously need two liquid phases entering our stabilizer. But for simplicity's sake in this webinar, I'm going to keep the trainment deactivated. Now let's take a look at our stabilizer. Right now, I just have an arbitrary boil-up ratio in my stabilizer at about 0.5. If you can see that little blurb right there, tells us that the boil-up ratio is 0.5. I also have a nifty little tool that I like to call the emission subsets that allows me to see what the emissions off my stock tank are. So this is a simplified representation of the contents of stream 3, which is my breathing losses, my emissions to the atmosphere. So as I'm currently running my stabilizer, I'm having 2,900 tons per year of BTEX losses, a very small amount of greenhouse gas losses at 2.52 times e to the negative 10 tons per year of GHGs or greenhouse gases, but my hazardous paraffins and my VOCs are 2,800 and 2.23 tons per year. So this is generally unacceptable for a lot of countries' environmental standards. So what I can do is instead of putting in a boil-up ratio, I can design or operate my stabilizer to target a particular RVP spec, a very common RVP spec. I'm using English units because I'm based in the United States and that's what we use here, but a very common RVP spec, and I think you guys might use this as well, is about 12 PSI. So if you hop into the stabilizer, under specifications, I can deactivate the boil-up ratio as a specification and instead activate the RVP as a specification. I'm setting it to an RVP of 12. And now let's see what happens when I re-execute the system. As you can see, all my breathing emissions, again, this does not account for filling or working emissions, go to 0 because my stock tank is at atmospheric conditions. So an RVP of 12 will have 0 breathing losses at atmospheric conditions. And I can operate the tower in such a way. If this was instead of a stabilizer was a stripper, where its main function was less to account for emissions in our tanks, but more to remove H2S content from our liquids, I can very easily go into the stabilizer and set an H2S content. I want 100 ppm or 50 ppm in my liquids going out of the system. Finally, I want to talk about how to generate our allocation report. Right now, here is the model we were talking about earlier. Again, I have 3 fields with their own associated produced waters going through a single compression system and separation system. So they all have their own inlet separators, but their second and third stage separations are all in one consistent system and they're all mixed together. We also have some knockout recycling. So each of our compressor knockout drums are recycled back into the third stage separation. And we have a general overhead gas knockout recycling back to the system. If I wanted to know how much of field 1 makes up my gas export, or rather, let me rephrase that. How much of my gas export is made up from field 1? This type of environment does not help me. Let's see what I mean by that. If I go into any stream, it doesn't really matter. I just want to take a look at the components. As you can see, it's just pure components. It's nitrogen, it's carbon dioxide, H2S, C7 star, C8 star, so on and so forth. They're all over the place, and all of my streams are represented as such. So that was field 1's composition. But if I go into a gas export, we can see that gas export is similarly represented by the individual components, the nitrogen, the methane, the ethane, so on and so forth. This does not help me if I want to figure out what the source of these components are. Did it come from field 1, field 3, so on and so forth? So what I need to do is create an allocation report in order to represent that. The allocation report in ProMax is done by utilizing our latest addition to our ProMax toolkit, which is in ProMax 5, which all of you guys should have available, which is the mixed species tool. Basically, you can create an environment that, or a component in the environment that has a certain mixture of components. This is especially useful for when you have blended amines, for example. A lot of you guys are sour gas technicians or sour gas process engineers. If you have amine blends, that's what the mixed species would be useful for if you have an amine blend. Another good use is if we define each of these systems instead of as individual components, but as a single mixed species of field 1. So I want to represent this entire composition as field 1. You could say, well, that's going to be a pain having to add the composition again and the whole 9 yards. That's fine, because what you can do is, since you've already added it once, you can right-click on any composition in ProMax. And then there is an option that says create a mixed species. So this is field 1. I'm going to create a mixed species with this composition and label it field 1. And I'm going to do the same thing for the 3 other fields. So field 2, create a mixed species, label that as field 2. Field 3, create a mixed species, label that as field 3. And finally, field 4. We can create a mixed species and label that as field 4. You want to take a look at all the mixed species that you created. This is what is called the project viewer. On the left-hand side, there is the project navigator, which has all of the blocks in ProMax. So every component, every stream, every compressor, heat exchanger, etc., etc. But it also has, let me minimize all of these miscellaneous terms, all our calculators, our solvers, and our specifiers, but also the mixed species. So here are all the mixed species in our system. I can go to each individual one and take a look at how it's defined if I want to change those definitions. Now, just like the oils, I need to add the mixed species to the environment. So instead of messing with this flow sheet that's been neatly done, I have duplicated the flow sheet, but as you can see and know if you have attended our training sessions in the past, most of these are red. Red means undefined. These streams don't have any information in them. And true enough, if I pop into field 1, for example, and go into the composition, only water is there. So we don't have any other terms in there aside from water. So I'm going to go into this environment and add the mixed species that I've created, okay? So if I hit active environment, under components, I have all of my oils down here on the left-hand side, bottom left-hand side. But I also have my mixed species. So I just need to scroll down and find them. There are my mixed species, fields 1 through 4. Can highlight all of them, add that to the environment, and hit OK. So now when I go back to any of these streams, we'll see under the composition tab an option to add field 1, field 2, field 3, field 4. So now it's as easy as we know that field 1 is obviously 100% field 1. So we go to field 1 and type in 100% in the composition. Field 2 is obviously 100% field 2. The same for 3 and 4. Now that I have all my systems defined, let me just go back through them. 100% field 4 for a quick sanity check, make sure my inputs are accurate. 100% field 3, 100% field 2, and 100% field 1. With that out of the way, I can execute my system. And ProMax is now smart enough to keep track of how much of each of these streams go into what stream. So it will know including changes in composition, how much of the streams have deviated. So if I go finally to my gas export, we can see that of my gas export, 48% comes from field 3, 43% comes from field 4, and 4 and 3% come from field 1 and 2. And in my condensate export, 52% from field 1, 13% from field 2, 19 and 14% for fields 3 and 4 respectively. So it's able to keep track of the changes as it goes on. Not only that, you can also figure out, it's like, okay, this is great. I have figured out how much of my gas export comes from field 1, how much of my gas export comes from field 2, but I'm not satisfied with that. I also want to know how much of the H2S in my gas export comes from field 3, for example. And that is fine, because if you hop into our gas export stream, you go to the Analysis tab, you can add a mixed species analysis. What this does is it breaks up the mixed species from just saying field 1, field 2, or field 3 back into its individual components. So in the mixed species analysis, there is our normal components for our mixed species, H2O, N2CO2, the whole 9 yards. So when we hit solve, this is the normal composition of our gas export stream in the individual components. Right? So now we can have our cake and eat it too. Not only do we know how much of our gas export comes from each field, we also know the standard composition of our gas export. And just to prove it to you guys, I'm going to go back to the pure species flowsheet where I don't have these mixed species. And here is my gas export composition without doing the allocation report. As you can see, they line up in terms of the content. There's a slight discrepancy because it's adding in water to the system, and water is all the way down here. All right, so you just need to counteract how that looks like. But it's the exact same composition across the board. Another thing to note is now I want to know not only what the content of my gas export stream is, but the source of each of these components. So if I go to expanded composition, you can see the composition from each component from each field. So using CO2 as an example, we can see that my gas export is 0.24% carbon dioxide that comes from field 1. It is also 0.14% carbon dioxide from field 2 and 1.9% carbon dioxide from field 3, and then finally 1.7% carbon dioxide from field 4. So not only do we know the overall composition, we know the composition of each component from each field. A simpler breakdown of this is under the partition tab. So as you can see, field 1 partition, field 2 partition, field 3 partition, so on and so forth. So what this does is basically telling you your nitrogen. 8% comes from field 1, 9% comes from field 2, 42% from field 3, 38% from field 4. Same thing for the CO2, same thing for the methane, so on and so forth. All right? So this gives you an even better breakdown of the system. Another thing to note is that I have disconnected the recycles in the system, right? So these recycles had knockouts. Some tools have trouble with recycles and allocation reports. But with ProMax, oh, I do not like that. I hate it when that happens. So let me fix that real quick. Much better. I can reconnect those recycle streams, re-execute my system. Now it'll iterate through and solve the system with our knockout recycles. Is it possible to know the percentage contribution of each source field in the final gas export. Yes, that's the first screen that I showed you. Let's just let this system solve real quick as you go through. But under gas export, in the composition tab, that is the contribution. So 4%, as you can see, it's iterating right now, but as you can see, around 5% comes from field 1, around 3% comes from field 2, 48 and 43% comes from 3 and 4 respectively. So that's the contribution of each field to the gas export, the overall stream. And then under the analysis, you can then see the contribution of each field for each component in the overall stream. So if I solve, so field 1 contributes 6% of the CO2. Field 2 contributes 3% of the CO2. 3 and 4, 47 and 42 respectively. So under the composition tab, there's the contributions for each of the fields to the overall gas export. And under the analysis tab, I have the contribution of each field for each component of my overall gas export. And now we can see that the system solved with the recycle just fine. And now we're still able to do the allocation examples. So the same thing that applies in the export gas also applies in the condensate export. Here are each field's contribution to the condensate export. 49% of the condensate comes from field 1, 12% from field 2, 21 and 16% from fields 3 and 4. And under the analysis tab, I can add a mixed species analysis, figure out what the composition in terms of pure components are, and also figure out the partition, the contribution of each field for each component. Let me see if I missed any questions. How can we do allocations with the lab sample correction you have done earlier? So this allows me to get the initial weld stream composition. So this lab sample correction gives me an initial composition, right? So what this gives me is the composition of field 1. After I have that composition, it's as simple as popping into, say, weld stream 3, right-clicking on that composition and creating a mixed species, and then labeling it what I need to label. So the lab correction is to just get an accurate input to your software. After that's there, you can create that, have that composition that you've corrected or manufactured be your mixed species, and then you can run the allocation. I hope that I was able to showcase some of the benefits and simplicities in terms of how to set up a allocation report and how to set up a general production facility.